So let us take few more question and answer in data structure and algorithms. So write short notes on the following: threaded binary trees, graph traversal, conversion of forest into tree, and doubly linked list. So threaded binary tree, just by changing the null values in a binary tree. Say if you have a node, now this node, okay, this node has null here and null here, so it has no left subchild or right subchild. It is a node or a leaf, you can say. So why not to put an address rather than having null, to put an address of the previous one? So by changing the null lines in a binary tree to special links, which is called as threads, it is possible to perform the traversal. Means why we are doing this, having the null value replaced by the previous address. It will help us to traverse, insert and delete without using either stack or recursion. This is very important. So in a write, in a threaded binary tree, each null link is replaced by a special link to the successor, to the previous one, or the next one, you can say, to the successor that node under in order traversal. So the successor in the in order traversal, called the right threaded. In using right thread, we shall find it easy to do an in order traversal of the tree, since we need only follow either an ordinary link or a threaded to find the next node to visit. So if you replace each null left link by a special link to the predecessor of the node known as the left threaded, under the in order traversal, the tree is known as left in threaded binary tree. The previous one was right in threaded binary tree. This is left in threaded binary tree. And if both the left and right threads are present in tree, that is known as the fully threaded binary tree. This is the example. Next is graph traversal, and we know that there are two types of graph traversal: depth first traversal and breadth first traversal. And traversal is nothing but traversing each node in certain way. So in many problems, we wish to investigate all the vertices in a graph in some systematic order. So in a graph, we often do not have any vertex singled out as special, like we see in tree. And therefore, the traversal may start at an arbitrary vertex. These are two traversing methods: depth first and breadth first. In depth first, DFT of a graph is roughly analogous to the pre-ordered traversal of an ordered tree. Suppose that the traversal has just visited, say, vertex. We let W0 to WK, let this be the vertices which are adjacent to V. So we shall next visit W0, and we keep W1 to WK, all these waiting from here to here waiting. After visiting this W0, we traverse all the vertices to which it is adjacent before returning to either W1 to WK. And we do it for W1 then recursively till we reach to the last node. So this is the, let me tell you the DFT of this graph. This is a graph, and the DFT traversal will be something like this. First we go to 1, and we see that 1, 2 is there. Then 2, we go to 3, 3 to 4. Now this is done. Okay. So we come to 2. Now we go to 4. And from 4 we can go to 6. 6 we can go to 7. 7 we will go to 8. Now this is also done. So 9 is remaining. So we will like that. What about the breadth first? This BFT of a graph is roughly analogous to level by level, each level of traversal in an ordered tree. So if the traversal has just visited, say, vertex V, then it next visit all the vertices adjacent to V. Putting the vertices adjacent to these is a waiting list to be traversed after all the vertices adjacent to V has been visited. So BFT of this will be, so we have gone to 1, then 2, and see 1 and 1 with 1, 2 and 9 are at same level. So we'll take 2 and 9. Okay. Now after this, 3, 5 and 6 are at same level. They are at say double edge difference from 1. These are 2 edges. These are 2 edges. So we take this 3, 5 and 6. After this, we see that 4 is of 3 edge distance from 1. So we take 4, then 7, and then 8 is remaining. So 8 we take. This is how we traverse the graph. Next is conversion of a forest into tree. How you are going to convert the forest into tree? A binary tree may be used to represent an entire forest, since the next pointer to the root of a tree can be used to point to the next tree of the forest. Again, we have the a binary tree which we are saying that may be used to represent the entire forest. How? Because the next pointer in the root of a tree can be used to point to the next tree of the forest. And this figure illustrates a forest and its corresponding tree. So initially, the left tree is represented as a binary tree Then the second tree is made the right child of the root node of the first tree, and the third tree is made the right child of the root node of the second tree. So let me again explain you what we said. This is a forest. Forest means just you can understand in a forest how many trees you can have. You have number of trees. So this area where you have number of trees, you call it as a forest. Just having an analogy with actual forest. Now how can you convert this forest into tree? And we said that you have a left tree. Okay, this is the left tree which is represented as a binary tree. Then you have a second tree, that is L. This is made as the right child of the root of the first. Root of the first. And made the right child of the root node of the first tree. And the third tree, you can, this is the first tree, this is second tree, this is third tree. So we are making G as the child of A. See? Okay. Now we have H, I, J, K according to the binary formations. And the third tree is made the right child of the root node of the second tree. So what is the root node of the second tree? G. So we are making this tree, the root node of L as the right of G. So now we have L here. So all these C, D, E, F will come here. Next will come here. All these nodes, and the formation will be, of course, the binary tree. This is the binary tree from the forest. Now double or doubly linked list. What is it? The doubly linked list or double linked list, also known as a two-way list. Why it is two-way list? Each node is divided into three parts: first, second, third. You know, every node of a tree, of a list is should have some initial address, that is head. So each node is divided into three parts. These are the three parts. The first part is the let's take the middle part first. Middle first part is the information. Of course, whatever we are doing for information only, for data only. This contains the data part. Now what about this left and right? Left contains previous pointer fields to the first node. That is the head here in this case. And the next pointer will that this field will point to the first node or this node. So the first part again is called the previous pointer field. It contains the address of the preceding element in the list. The second part contains the information. The third part contains the next pointer field. So it contains the address of the succeeding element in the list. So in addition, we have two pointers which are called as head and the tail. They are used that they contains the address of the first element or the address of the last element of the list. The doubly linked list can be traversed in both directions. Differentiate between system-defined data types and abstract data types with suitable examples. Abstract data types, as we have seen, this is just you have a mathematical and logical representation of data along with certain operations which are supposed to be done on them, like stacks and queues, etc. We have two parts: value definition and operation definition. We have already covered this a lot, so I'll not be able to elaborate it. We have seen in greater detail. But what are system defined data types? See, these are the data types that have been defined by the compiler of any program. Like C language has four basic data types: integer, float, character, double. So these are four qualifiers that can be applied to integers, say short, long, unsigned. A variable design declaration in C specifies two things. First, it specifies the amount of storage that must be set aside for an object declared with that type. This is very important. Second, it specifies how data represented by strings of bits are to be interpreted. The sum bits at specific location can be interpreted as an int of a floating point number, yield two completely different numeric values. So it is not possible to implement a particular ADT on a particular piece of hardware or using a particular software system. Explain the following: complexity of an algorithm and the space-time trade-off algorithm. So complexity, we know the time complexity and space complexity, because an algorithm is a sequence of steps to solve a problem. So there may be more than one algorithm to solve a problem, or maybe you can have number of algorithms. So how you are going to define or decide which is the best? You go for the complexity. So the choice of choosing a particular algorithm, which is to be considered, is based on the time complexity and space complexity. Time complexity of an algorithm is the amount of time it needs to run to application. Some of the reasons for studying this time complexity are: we may be interested to know in advance whether the program will provide a satisfactory real-time response. And the second is, there will be several possible solutions with different time requirements also. Then comes the space complexity. The space complexity of an algorithm is the amount of memory it is going to need while it is running. some of the reasons why we would require this space complexity. There may be several possible solutions with different space requirement. And to estimate the size of the largest problem that the problem can solve, this is also for space complexity. Now, what do we mean when we say space-time trade-off algorithm? So the best algorithm to solve a given problem is the one that requires less space in memory and takes less time to complete its execution. But in practice, it's not always possible. So there may be more than one approach to solve a problem. One approach may require more space but less time to complete its execution. The other approach may do the vice versa. So we choose the first approach if the time is a constraint, and second if the space is a constraint. So this we may have to sacrifice one at the cost of the another, and this is where we can say we are doing some time-space trade-off. Define a sparse matrix. Explain different types of sparse matrix. Show how a triangular array is stored in memory, and evaluate the method to calculate address of any element ajk of a matrix stored in a memory. So sparse matrix, as we have seen, that most of the contents are 0. So m by n matrix A is said to be sparse if most of the elements are 0. So a matrix that is not sparse is called a dense matrix. These are the types of sparse matrix. This is a diagonal matrix, means only diagonals or principal diagonal elements are 1, otherwise all are zeros. This is a square matrix where the non-zero elements are only where row equal to column, or Aij where I equal to j. That is the diagonal, that is called the principal diagonal. This is tri-diagonal matrix. What it means is, in this square matrix, all elements other than on and on the diagonals immediately above and below, these are non-zero. These are below this one are 0. What it means is, we only have these elements, one principal diagonal, then above it and below it. So in this is again a square matrix. All elements other than those on the diagonals immediately above and below, all are zeros. So we also have triangular matrices, because these are also known as the sparse matrices type. We have lower triangular. Lower triangular means only the contents are in the lower part, and the values above the principal diagonal, they are all 0. In the upper triangular matrix, all the values which are upper or above the principal diagonal, this diagonal, are numbers, otherwise all are zeros below. So in a n by n lower triangular matrix, row 1 has one non-zero element, row 2 has 2, and likewise. So whereas in n by n upper triangular matrix, row 1 has n non-zero elements, row 2 has n minus 1, and so on. So in both the cases, the total number of non-zero element is what? N plus 1 by 2. You can easily find it out. Total number of non-zero elements for n by n matrix. So both of these matrices can be represented using a one-dimensional array. Say LA of size n plus 1 by 2. So just consider a lower triangular matrix L. The element can be mapped by rows or by columns. So in a row-wise mapping, the element Lij, where I is greater than or equal to j, is preceded by k, for k equal to 1 to I minus 1. And elements that are in the row from I to through I minus 1 and j minus 1, each element from row I we take. The total number of elements that precede it in a row-wise mapping is I minus 1 by 2 plus j minus 1. So this expression also gives the position in LA. So how we can have a method to calculate address of any element ajk of a matrix stored in a memory. So let us just consider two-dimensional array, say A of size m into n. Further, consider that the lower bound of the row index is LBR and the column index is LBC. So like linear array, the system keeps track of the first element only, nothing else. That is the base address of the array. Using the base address, the computer computes the address of the element in the ith row and the jth row. How? Location of Aij. So using the formula, column, this is the matrix, if you place column by column, this column in the memory, or row by row, so column major will have location as base A plus W m into j minus LBC plus I minus LBR in general. And we know that LBR and LBC is what we have just seen. And similar for row major order, location Aij will be base A plus W n I minus LBR plus j minus LBC, where W is what? It is the number of bytes per storage location for any one element of the array. Now, a linear array A is given with a lower bound as 1. If the address of A25 is 375 and A30 is 390, find the address of A16. Okay. So the question is saying then you have a linear array which is given with the lower bound as 1. Okay, lower bound is 1. So address of A25 is 375 and A30 is 390. That is A30 is what you have 390. So you can see 5 variations. So if these values are, there are 5 values in between. So 375, 390, you can easily find out the difference, and you can find out that 390 minus 375 is nothing but there is only a difference of 15. Okay, so there is a difference of 75 to 90 as 15, and how many values are there? 5. So 5. So each will be taking 3 bytes or 3 units. Find the address of A16. You want to find out A16. So what is the difference between A16 and A25? That is how many numbers or how many values will be there? 25 minus 16. It will be 9. 9 3 is 27. So this is what we can get. But let us see the actual value which is coming. So we know this formula. Location of AK is base A plus W minus K LB, and LB is given as 1. The base A for 375, first is 375, and K is 25 for this case. So it will be 25. Let us see for the second one also. This is 3390. A30 is at 390. So base A is W30 minus 1. We solve it. We get W equal to 3. As I said, we have, this is the 3. Now let us see what is the X. Just place it anywhere. That will be 375 minus 24 into 3. So X is 303. So we start from 303. Okay, 303, and we know that base address is 303, and W is, the width is 3. So we have this A16. So just place it in this formula, this one. So it will be 303, that is the base address, plus 3, that is the width, plus 16 is given, minus 1, 348. And this is 348. Let me add this, let me subtract 375 from 348, and it will be nothing but 7, and that is 2, that is 27. So 9 3 is 27, as we guessed earlier. 9 3 is 27, the value is exactly same, which we got. Now the next question is, we have 8 numbers and we have to construct the binary by inserting the above numbers in a given order. So first 50 has come. 50 has come. 50 will be placed here. There is no choice. Now 33 is there. 33 is greater than or less than 50. It is less than. So always less, the value which is less than the upper node will be placed here, which is less than, and the value which is greater than will be placed here. So we'll follow this rule only. 33 will be placed here. 44 has come. Now this is our node of concern. 44 is greater than 33. So where it will be placed on the right. Same logic. 22 has come. 22 is less than 33. So it will be placed. This is less than. So we'll place it on the left side. So 22 will come here. This is our binary tree. Now we have 77. 77 is greater. This is done because this has become binary. Now we are left with the right one or left one. Of course, there is no left one because 50 has already taken left. There is only right. So 77 is greater than 50. So we'll place it on the right side. So this is how 77 is placed. Now 35 is there. Where you are going to place, because all these are filled. So let us place 35. 35 will be placed because this 44 has no left and right. But 35 is of course less than 44. So you can place it here. 35. Now 60 has come. 60 is greater than, because of course 77 has a place left and right. So 60 will be given to 77. That is 60 will be made as the right of this value. And then we have 40. How are you going to make 40? 40 will be placed on the right of 35. So this is the binary tree which we made from the input values. So in this case, what we have started, you will be surprised, of this step. But let me change it, because it is very necessary to understand that in the final subtree, for final tree, every node, if 55 is C, all the node on the left, it is less than 55. All the nodes on the right, they are greater than 55. But in this case, 77, we have 60 which is on the right, which is less, so we'll make it here. We'll drop it. So there's a change. We will make it as left child. Now all the values, you take any node, you take 77, all the values are on the left are less, right we don't have. And in 33, say take any node, you'll find it. So this is how we make the binary tree. Binary search tree actually it is. Can a queue be represented by a circular linked list with only one pointer pointing to the tail of the queue? Substantiate your answer using an example. Can a queue be represented by a circular linked list with only one pointer pointing to the tail of the queue? Yes. How? A queue can be represented by a circular linked list with only one pointer pointing to the tail of the node. For example, this is in picture you can see this queue has a pointer pointing to the tail of queue, to the tail of queue, and this pointer represents the real of the x, that is and which is the value, which is real part, and the pointer next is the front of queue. Okay. Establish the usage of linked list for polynomial manipulation. This is we have already seen example of this in the previous question. So the usage of linked list for polynomial manipulation is like this. Linked lists are frequently used for maintaining the polynomial in memory, and the polynomial of say 4x cubed plus 6x squared plus 10x plus 6, this is x to the power 0, which can be represented as, we take coefficient and the power, coefficient and the power, coefficient and the power, coefficient and the power, and this is null. So where we have what we have done is, first one is the coefficient, the second one is the power of x, and third is the null. This is linked to the next node. A linked list can be used for adding the two polynomials. Convert the following infix expression to postfix. So this is the final solution, and we have done a more detailed question of solving them. So I hope that you can get the answer. Explain the hash table, hash function, and hashing techniques. We have seen hash also, but you see, hash is so important that this is always the favorite question for the interviewers and the examiners. So we'll take more of it. What is a hash table? A hash table is a data structure in which the location of data item is determined directly as a function of data item itself rather than by a sequence of comparison. So we get the order of 1 time. Under ideal condition, the time required to locate a data item in a hash table is order of 1. That is, it is a constant time and does not depend on the number of data items which are stored. So when the set k of keys stored is smaller than the say universe u of all possible keys, a hash table requires much less storage space than the direct address table. Now what is hash function? How you are going to find the values or access the records in order of 1? For that you have to have a hash function. So hash function is simply a mathematical formula that manipulates the key in some form to compute the index of this key in a hash table. For example, a hash function can divide the keys by some number, usually the size of the hash table, and return the remainder as the index for the key. So in general, we say that a hash function h maps to the universe q of keys into a slot from 0 to say n minus 1 of hash table. So in the process of mapping keys to appropriate slots in a hash table, we know it as a hashing. So we have main consideration for choosing the hash function. It should be possible to compute first of all efficiently, and it should distribute the keys uniformly across the hash table. That is, it should keep the number of collision as minimum as possible. In this hashing techniques, there are a variety of hashing techniques. Let us see this division, that is k mod m. In this method, the keys, k keys are mapped to one of the m states. Multiplication method means multiplication method operates in two steps. In the first step, the key value k is multiplied by some constant k, a, in the range from 0 to 1. And the fractional part of the value obtained is multiplied by m. And the floor of the result is taken as the hash value. And this is the hash function. So ka mod 1 means the fractional part of ka minus ka. And this is the floor. For example, 5 minus 1 by 2, which is given by 0.61 or some value. So we have also mid square method. This operates in two steps, and in the first step the square of the key value k is taken. In the second step, the hash value is obtained by deleting digit from the end, and the squared value is k square. So the hash function is something like this, where s is obtained by deleting digit from both sides of k square. So you have list, you square it, and you discard these values, so you take this only. Define linked list and how are these stored in the memory. Suppose the linked list in the memory consists of numerical values. Write a procedure for each of the following: to find the maximum max of the values in the list, to find the average mean of the values in the list, and to find the product of the values in the list. So first you have to define the linked list. How are these stored in the memory? And we need to suppose that the linked list in the memory consists of numerical values, and we have to write the procedures. So linked list is a linear collection of data elements called nodes, and the linear order is given by the pointer. Each node is divided into two or more parts. A linked list can be of various types. That is one-way list, linear linked list, two-way list, double linked list, circular linked list, and header linked list. So the representation of linked list in memory would be like this. Every node has a information part, and a pointer to the next called the link. The number of pointers in they can be 2 like this in the double linked list. You have a header always pointing to the first node. An external pointer points to the beginning of the list, which is this. And the last node is null. We show it as ground. So the space is allocated for nodes in the list using malloc and calloc functions. The nodes of the list are scattered in the memory with links to give linear order to the list. This is the max of function. This is the min of function. And this is the product of function. And these are self-explanatory. So I leave you to understand this and you can also implement it by yourself. So these were a few questions again on our data structure and algorithm. We are going to see more of it. Thank you so much.